Datemi il via, vediamo un po'. Cominciamo, cosa dite? Sì, I think everybody is here. The first talk of this last section is devoted to interaction between mathematics and crystallography, but I think it was evident from the previous talk that mathematics have an important role in quasicrystal theory and practice. Speakers are Paolo Boggiatto and Alessandro OLIARO, speakers from our Department of Mathematics of the University of Torino. They work in a new field of mathematical analysis, which has a precise label name and is Fourier quasicrystals. Of course, it's a point of view of strictly mathematical point of view, but the name is exactly contains exactly the words quasicrystals. And if I can say something more about, in general, applied sciences give to mathematics new ideas and challenges. But in return, as I have seen, it happens, mathematics, beside giving a precise interpretation of the problem, provide some suggestions for new achievements in applied sciences. Excuse me, I give the word first to Paolo Boggiatto. Please, Paolo. The title is Mathematics of Quasicrystals.
Well, first of all, thank you very much to all the organizers for the wonderful chance to take part in this workshop and to meet this research group. Together with my colleague Alessandro, we will talk about some aspects of mathematics modeling quasicrystals. So I beg your pardon, there will be some formula, but not too many. Let's start by saying that Fourier analysis is the main mathematical tool everywhere we have to do with frequencies of signals structure of some physical phenomenon. And when these frequencies are varying in time, the natural evolution of Fourier analysis is time-frequency analysis. Whereas classical Fourier analysis is a well-established practice in the study of quasicrystals, we would like to present an approach which makes use of time-frequency analysis in the study of quasicrystals. This has led us to some results we have obtained in collaboration with two mathematicians of the University of Valencia in Spain, Antonio Galbis and Carmen Fernandez. Here is the plane of the talk. I will give a general panorama at first, talking about frequency and Fourier transform, then the adaptation to the Gabor transform, and finally the generalization to the Cohen class of time-frequency representations. After this general presentation, my colleague Alessandro will talk more specifically about Fourier quasicrystals and their treatment with tools from time-frequency analysis. So, we start from the very beginning, from the very basic viewpoint. We know from the high school that any times where we have a structure or a phenomenon which repeats itself after time or space t, and so it's modeled by a function with period t, we associate a frequency which is 1 over the period, so 1 over t. This is very elementary, but of course it's a naive rule that fails almost immediately. Let us just have a look at this function here, the sum of two cosine functions. The first is period 1, the second is period the reciprocal of 5 over 4, so 4 over 5. And it's an easy calculation. The two functions go into phase every 4 units. So the period is 4, and we should associate the frequency 1/4, which makes no sense actually, because the phenomenon is represented by these two different frequencies. But something even worse can happen. Let's have a look now. If a second function is of this kind, then the period is 1 over square root of 2, so it's irrational, and apart from 0, the two functions will not go into phase again. And so this is not a periodic function, and we don't have any frequency to associate. And still, the phenomenon contains these two different frequencies. By the way, I will loosely speak about functions. My colleague will be more precise in the specification of the functional setting. I just want to give a panorama in this first part. Fortunately, we have, of course, a wonderful tool, which is the Fourier transform, to overcome this problem. Here is our definition of the Fourier transform. The normalization we take is with the one with 2 pi at the exponent. Okay, this is usual for signal analysis. And for instance, in this case of a signal of this type, it says absolutely no problem to distinguish that it contains 4 frequencies corresponding to these 4 peaks. But of course, here it becomes also the troubles, because as soon as we plot the Fourier transform, we have to plot a function which has complex values. And so we have to take the absolute value of this complex number. More precisely, we take the square of the absolute value in order to preserve energy. And we lose something. We lose some information. The information we lose is essentially the information about when the frequencies appears in the signal or in the structure. The retrieval of the signal or the original function can be difficult or even impossible. Let's see this case. Here, the retrieval is very, very difficult. We have two different signals. In the first one, we have 4 frequencies, which are played, let's say so, played in a sequence. In the second time, we have a second signal. We have the same frequencies, which are overlapping. And the two Fourier transforms are very, very similar. It's almost impossible from the form of these peaks to retrieve the signal. Then there is a case, a very easy case, where the reconstruction is even impossible. And it is the case of a simple translation. If I translate a signal and I take the Fourier transform and I consider the absolute value of this transform, they are exactly identical. So this is impossible to, to distinguish from which signal it comes. The idea to overcome this problem essentially came from Dennis Gabor and his collaborators. And the idea was to cut the signal before taking the Fourier transform. To cut the signal by multiplying the signal with a window function g, in such a way that only the part of the signal falling into the support of this window function is then transformed and analyzed. And then we can translate by the parameter x the window and analyze the whole of the signal in the time. We get, of course, a function of 2 variables. X is the time and omega is the frequency. Here is a picture, let's say a cartoon. We have a function f which shows a lower frequency in the first interval and a higher frequency in the second interval. As a window, we choose here a Gaussian window, and the multiplication of the two just gives this third graph, where only the part of a signal inside the essential support of the window is visible. And so we can translate and analyze the whole signal. As we have said, we have a function of two variables, so a surface. Here is the surface in our case, and here is the time axis, and here the frequency axis. We clearly recognize in the first interval the lower frequency, sorry, and in the second interval the higher frequency. If we look this from above, we have this picture, which is actually the exact mathematical correspondent of a musical score. So here's the first note, and here the second note. Okay. Also here we take, of course, the absolute value, more precisely the square of the absolute value, because also the Gabor transform is a complex number usually. We have anyway a representation of signals or structures or phenomenon with respect to both time and frequency. So we have a time-frequency representation. Okay. The choice of the window is fundamental, and there is a huge amount of literature about properties depending on the window. But there is this is not the only way to create new time-frequency representations. Another very simple way is to observe that the square of the square of the absolute value of a complex number is just this complex number multiplied its complex conjugate. And so there is no need at all to take the same window here and here. We can choose two different windows, and we can so generalize to this kind of representations, which are called generalized spectrogram. To this regard, for mathematical convenience, usually we also suppose to have two different entries, F and G here. And of course, if F is equal G, and the two windows are the same, we get the usual spectrogram. But this is a very common situation in our field in mathematics. We have, where we often have a sesquilinear form, let's call it Q, of two entries, F and G. And this yields a time-frequency representation by choosing F equal G. So it's Q of FF, which we for shortly write Q of F. So now let's change our point of view. We could want to have something more intrinsic, not depending on a window. And there are at least two very important cases of time-frequency representation of this type. The first one is the Riaszek representation, which is the most easy representations of all, I would say. It's just the product of a function, f, and complex conjugate of a Fourier transform of the second entry. And the two are tied by this complex exponential. It's very easy, it doesn't involve any integral, and it still gives information about time and frequency. But the most important of all, I would say, is the Wigner representation, which is defined in this way. It was introduced by Eugen Wigner in the context of quantum mechanics. But as you know, quantum mechanics and time-frequency analysis share a lot of mathematics, I would say most of the mathematics. And so this is widely used also in time-frequency analysis. And finally, coming to the Cohen class, more generally, all the representations we have seen so far are members of this wide, broad class of time-frequency representations. Here, the idea is to smooth the Wigner with a convolution, Here is the formula, the Wigner, convoluted by a sigma. Sigma is a distribution which is called a Cohen kernel, and it permits to balance between different properties or drawbacks of Wigner distributions according to the choice of the kernel. Let's have a summary here. The Wigner is, of course, a member of this Cohen class. It's enough to take a convolution with the delta function, which is the identity of the convolution. But every generalized spectrogram is also a member of this class. In this case, the Cohen kernel is again another Wigner, and precisely the Wigner of the two windows exchanged in order and with a reflection in the variables. And finally, also the Riastek representation is expressible as a member of the Cohen class, and in this case, the Cohen kernel is a complex exponential. Then there are, of course, many other choices according to the practical situation. To this regard, I had some fun by asking ChatGPT to compare the spectrogram, the Wigner, and a little bit absurdly the general Cohen class with respect to some properties. We don't need to read everything, but just have a look, for instance, at the first line, cross-term interference. Well, this is a very big problem of the Wigner representation because, loosely speaking, the Wigner puts a ghost frequency between any two real frequencies. And so, due to this, the presence of these ghosts, the interpretation sometimes is difficult. This does not appear, this problem does not appear with the spectrogram. So, correctly, ChatGPT answered every question here. And here it says yes and here no. But if you have a look at the third line, high resolution, we see that the Wigner has a very good, neat resolution, whereas the spectrogram sometimes is very, let's say always is more or less blurred by the presence of this window. And so by choosing the right kernel, we can balance, and here actually the expression of ChatGPT is something between the two characteristics, and we can choose the most suitable representation for any practical situation. Okay, and finally, I must admit that not all the interesting representations, time-frequency representations, are in the Cohen class, and there is a very significant example. It is the radar ambiguity function. It is defined in this way. It does not belong to the Cohen class. It could seem quite similar to the Wigner as we see here, the definition, but there is a very crucial difference. The integration here is taken with respect to the first variable here and not to the second, and so there is a crucial difference. I have done with my presentation with the general panorama. I hand over to my colleague Alessandro OLIARO.
Okay, then going to something more related with quasicrystals. What about the mathematical definition or a mathematical model for a quasicrystal? There is not a univocal definition or model of a quasicrystal from the mathematical point of view. Different models can be found in the literature. And we will focus on one model that is called Fourier quasicrystal. This is characterized, of course, by means of the Fourier transform. The main point is the Dirac delta distribution. That is something that is used, usually it is used to represent some amount C, where C is the coefficient that we put in front of the delta function of some observable concentrated at some point delta. And then it is quite natural to represent a quasicrystal as a sum of Dirac deltas with eventually with some coefficient, and this sum could be infinite, and each term corresponds to an atom or a molecule located at the position xn. Of course, for a crystal, the positions are arranged in a periodic way. For a quasicrystals, the position may be arranged in an aperiodic pattern, but still following a longer range order. And what about the Fourier transform of such a sum? The Fourier transform of a single Dirac delta is a wave function of this form, something that oscillates. But if we consider an infinite sum and the points are sufficiently, let's say, well distributed, then the Fourier transform of the entire sum is again a sum of delta multiplied by some constants. And the location of the values omega k matches exactly the diffraction pattern of the quasicrystal. Which is again a discrete aperiodic set with some long range order. And so, without coming deeply to technical mathematical details, a definition of related to quasicrystal that was given by Lev Dolevsky is this definition they call the Fourier quasicrystal, a tempered measure that is of this form, a sum of deltas located at some point, for which the Fourier transform is again a sum of delta located at some other points. And these sets, capital lambda and capital S, are supposed to be discrete subset of Rn. Okay, one example, the simpler example is in fact something that is completely periodic, the Dirac comb. We take a lattice and delta located at the point of the lattice. And in this case, the Fourier transform is again a Dirac comb. The coefficients, we may take the coefficient, all the coefficients equal to 1, and the Fourier transform is again a Dirac comb located at some other lattice. But of course, we are interested about the structure of a Fourier quasicrystal in the general case. And if something related to some structure that is not periodic may appear in this kind of mathematical models for quasicrystals. We need a definition that is the definition of a set that is uniformly discrete. This is a condition that is often considered in the study of quasicrystals from the mathematical point of view. It means that the points of this set are sufficiently well separated one each other. There is a minimum distance delta, and two different points cannot be must be sufficiently far. The distance must be greater than delta. And then there is a theorem due to Lev and Dolevsky that proved that if we consider a Fourier quasicrystal and we suppose that both the support and the spectrum of such a quasicrystal are uniformly discrete, then this is the structure. Mu must be of this form. So there is a lattice, there are translations of this lattice, and there are coefficients. Of course, these coefficients are trigonometric polynomials, so of some particular form, and of course some of these coefficients may be equal to 0, even infinitely many coefficients may be equal to 0, and moreover the coefficients themselves can be different and can have a periodicity that is incommensurable with respect to the corresponding lattice, and so this may produce a strong non-periodicity of this object. Still, of course, having some structure and some order, some long range order. Then what about Fourier quasicrystals and time frequency analysis? This theorem that we have seen requires conditions that are symmetric on a distribution and its Fourier transform separately, and then describing the structure of the Fourier quasicrystal. On the other hand, a time frequency representation, as we have seen in the first part of this talk, gives a joint distribution of the energy of mu with respect to frequency and time, and then it summarizes in one single object information from both mu and the Fourier transform of mu. And then a quite natural question is if information on a Fourier quasicrystal can be deduced from the knowledge of its time frequency representation or of one of its time frequency representations, since there are many different possible representations of a distribution. And moreover, if there are time frequency representations that detect in some sense in a better way a Fourier quasicrystal. We studied this problem in collaboration with Professor Fernandez and Galvis from the University of Valencia, and the results are of this kind. This is a first result concerning the Wigner, the classical Wigner transform. Supposing that the Wigner transform of a distribution mu is of this form, so it is a sum of delta located at some points. These points belong to a Cartesian product, and A and B are supposed to be uniformly discrete sets. Then mu is a Fourier quasicrystal with uniformly discrete support and spectrum. And then from the results of Lev and Dolevsky, we have a corresponding structure of the distribution of the quasicrystal mu. But we have seen that there are many different time frequency representations, and results of this kind can be proved in a more general frame and with different kind of representation. From this point of view, a good class of representation is given by this one that is called the matrix Wigner transform. It depends on a matrix T, and in particular on its submatrices A0, B0, C0, and D0. It is defined in this way. It has a definition that resembles the definition of classical Fourier transform, but it is interesting because it includes most of the basic time frequency representations that are used, and it has as relevant examples the classical Wigner transform and the radar ambiguity function obtained for these choices of the matrices. And what about results on Fourier quasicrystal related with matrix Wigner transform? We have two kinds of results where the results are always of the same type. We suppose that the matrix Wigner transform has this form, sum of deltas at some points of a Cartesian product, and we deduce that the mu is a Fourier quasicrystal with with uniformly discrete and spectrum. I would like to underline a few differences between these two results. First of all, there are conditions on the matrix. These conditions are in such a way that these two theorems apply to disjoint subclasses of the matrix Wigner transform. Moreover, here in the first result, we suppose that the R and S are uniformly discrete. In the second one, we just suppose that the R and S are discrete, that is less, of course. Moreover, in the second result, we may deduce also, in the general case, the structure of the corresponding Fourier quasicrystal. So, in some sense, the second result is a little bit better, in the sense that it requires less and it permits to conclude more. And the interesting, so the representation in the second result, in some sense, are a little bit better to detect Fourier quasicrystals. And as an observation, a relevant example satisfying the conditions of the first theorem is the classical Wigner transform. And a relevant example of a one satisfying the condition of the second is the radar ambiguity function. So in some sense, it seems that there, from this point of view at least, that the radar ambiguity function is a little bit better to detect a Fourier quasicrystal among the time frequency representations. And this is all we wanted to say. Here there is a short list of references. I would like to thank again the organizers for the opportunity to give this talk, and of course all of you for the attention. Thank you.
To respect the schedule, maybe also in this case we will meet questions, if you agree. Okay, then thank you again.
Okay.
Let me begin to say some words about the next speaker, Peter NEMETH, from the Research Center for Astronomy and Earth Sciences, Hungarian Academy of Sciences. I had a look to your two papers, which are many, and most of them, maybe most part of them devoted to quasicrystals. If I have well understood, there are two aspects. One, to discover in natural sciences existing or quasicrystals, and the other also interesting to produce industrially maybe quasicrystals. I think your talk now is in maybe the first direction, and the title refers the carbon case. Yes.
Thank you very much.
Please.
And I also thank the organizer for inviting me, especially to Professor Luca Bindi and also Professor Giovanni Ferraris. He used to be my supervisor here, so I spent a couple of years in Torino, and I really learned a lot about Professor Ferraris, about modularity and polysome series. Anyway, I am working with carbon, and you know, carbon may seem a simple element, but it still occurs in several forms thanks to the hybridization. If you look at the database, there are more than 200 structures you can find, and obviously most of them are theoretically calculated structures, but there occur also in naturally several forms. And I use transmission electron microscopy for characterizing them, and this Ariane demonstrated. This is a kind of useful technique for the characterization of materials, especially because we can investigate the bonding structure of carbon and also study even the atomic structure of the carbons, and even reveal really interesting patterns which you can see on the first slides, which shows unique, also unconventional symmetries. Here we see the 5-fold and 12-fold symmetries, which seem unconventional, but they occur in everyday life. In our everyday life, if you think a half-cut apple has a 5-fold symmetry, it shows a 5-fold symmetry, or a cacti shows 8-fold, a 12-fold symmetry. So anyway, in my talk, I will present some of these structures and also interesting structures which are difficult to handle them with the classical crystallography. So when I was a student, I learned that crystal is a solid material whose constituents, the atoms, molecules, and ions are arranged periodically in 3 directions and according to repeating patterns. And if you think about a nice quartz crystals, it's really, it fits into this category. But then in the 1980s, scientist Dan Chapman demonstrated that there are crystals which are ordered but aperiodic and cannot be described with this classical definition. And as yesterday Luca demonstrated that there are natural quasicrystals, in particular this icosahedrite. And in addition to those, we know that there are lots of modular crystals, lots of incommensurate structures in nature. If you think about the feldspar, the plagioclase, there are lots of them. So IUCR came out with a definition which is quite useful for describing this material. So it says is a material is a crystal if it has essentially a sharp diffraction pattern, and the diffraction could be in electron, neutron, or X-ray. So this seems quite a good definition because we could handle with these crystals. However, I still think it's not appropriate. There's still some issue because we say what is essentially. So in one of my slides, I will show you a crystal, which I think is a crystal, but has problem to categorize within this framework. Okay, so as I mentioned, I'm working with carbon, and as you know, carbon has 2 allotropes which are known from antiquity. One of them is the diamond, which came from the indomitable one, the Adamos, which is has a very high hardness. And then in contrast to them, we know there is graphite, which is used for, which is on the Mohs scale, it's a soft material, and words come from the writing, the graphene word. And as I mentioned, so it's quite a soft material. In the Mohs scale, its value is 1, and it's a very good electric conductor, and its density is 2.28. And according to the phase diagram, this is the stable form. However, if you have and high pressure is the high pressure phase. However, if you have a diamond ring, you don't need to worry about that it would transform to graphite unless you heat it up. So anyway, graphite is used in several applications, used in high temperature crucibles. It is an extremely high melting point. It could reach, I think it's 4,000 degrees C. It's used in anodes and is an excellent lubricant, resistant to acids. In contrast, the diamond has high hardness. On the Mohs scale, its value is 10, so the very high hardness, and it's an excellent thermal conductor. However, it's a wide band gap insulator, so in contrast to graphite, and its density is higher, and it's used in application in cutting, grinding tools, as well as protective layers. In addition to these forms, in the last century, we learned about there are other things. If you think about the graphene, which is a bidimensional material consisting of the honeycomb arrangement of carbon atoms. And I will use the word graphene when I'm talking about 1,5 layers. If it's more than 5, I would say graphite. So anyway, when these graphene layers, they could roll up and they could form nanotubes. We know that there are single, double, and multiple nanotubes. And these materials are known even from meteorites. Here is an example from the Tagish Lake meteorite. But in addition to nanotubes, by rolling them up, they could form even beautiful nanoonions. If you look at the panel A, you will see like a half-cut onion, right? It was rolled up. I think it's rolled up by these graphene layers. You know, nice examples. In addition to these structures, we know that carbon also occurs in fullerenes, which is practically the framework of 5- and 6-fold pentagonal rings, and they also were found in meteorites. Now, if a fullerene is included within a nanotube, we know there are these structures also. This is the so-called P-pod fullerene, and it's used in the industry where people are making it because it has interesting properties. It can be used for superconducting quantum computers or nanopipettes or even storage devices. And there is a similar structure we found in a meteorite, in the Gujba meteorite. I would like to point out in the lower panel, there is a cage structure, and within the cage we found a tiny diamond, which is called the Becky diamond. And this Becky diamond has properties similar to the fullerenes, and you know, you could ask, why is it interesting, why is it important? Because the fullerene type structures has an absorption at 217 nanometer, and they could possibly provide even explanation for the broad feature that occurs on the interstellar dust ultraviolet absorption spectrum. So in addition to this order structure, we find even amorphous carbon in meteorite, and here are some examples. These are nanoglobules, and some of them are empty or previously may contain some gas, which during the sample preparation they could have lost. Or even there are examples for amorphous carbon. So what I would like you to focus on in the next slide, I'm interested in the complex diamond structures. I mean, this diamond structure forms in two ways. We know two ways. One is the asteroid impacts, which such an impact could occur in the space or on Earth. And it's a nice example here in this meteor crater in Arizona. And from this side, an interesting material was reported in the 1960s. I will show some studies about what we found in this material. But the complex diamond structure, which I will present shortly, they also occur in nanodiamonds. These nanodiamonds are known in carbonaceous chondrites, and they are made of 2-5 nanometer sized grains. And in compared to the impact diamonds, they formed in low pressure. In fact, they formed from carbonaceous hydrocarbon gases in the method called process called chemical vapor deposition. Here are some examples. So this interesting complex diamond structure, which I will show you, they occur in these two types of diamonds. Okay, so yesterday we heard that the diamond was the first one which was described using X-ray in the last century, and the structure of diamond can be usefully described by the Packard arrangement of carbon, Packard hexagonal rings of carbon, and there are two types of arrangement, depending on how these layers are arranged in the 0-1-1 direction. There is the chair type arrangement, which give rise to the cubic diamond, and it's repeats. So this is the ABC, or the cubic diamond. However, there is another type, which is the boat type conformation, which give rise to the hexagonal diamond. And if you think about the structure, we think they are repetitive. They occur in at least some kind of longer range. And if there is there is one layer within one hexagonal layer within a cubic diamond, that's, we would say, a defect. Anyway, hexagonal diamond, that's the material which was reported in 1967 from the Canyon Diablo meteorite I showed you previously. And the scientists were intrigued by this material because since then they associated with asteroid impact and used it for explanation. And here are some examples in the diamond nanocrystal. And here are some examples in the diamond nanocrystals. Actually, in the panel I am showing a polysynthetic twin. However, these twins, if you're talking about nanocrystal, they could form even a beautiful star, and they show a 5-fold rotational symmetry, which more or less resemble the shape of this half-cut apple I showed even in the first slide. Anyway, when I was talking about investigating this Canyon Diablo material, which was called Lonsdaleite, when we using transmission electron microscopy, we found that there are abundant defects within the cubic diamond layers. But the point I would like to make that these hexagonal diamond layers occurs as up to 2-4 layers. So we would rather say they are defects within the diamond lattice, or in fact they form a unique material. On panel B you could see the structure of the material, and we give a unique name, is the cubic hexagonal stacking disordered diamond. And in fact, the Fourier transform of an HRTM image, like I'm showing on A, we would see the continuous streaking of reflections. And this material is quite unique. It's not in the nanoscale. The cubic symmetry is lost, and there are some consequences for that. And if you consider that there are this complex, we found this complex 0-1-1 integrals. I mean, 0-1-1 plane, it shouldn't be part of a cubic symmetry. Well, it's part of the cubic symmetry. It shouldn't be a mirrored plane, although we are seeing it in HRTM images and also on the Fourier transform, because it is a result of this defective structure. In fact, if you look at panel B, you will see two sets of streaking which are rotated 55 degrees respect to each other. And on the panel C, you could see the structure model for such a 0-1-1 integrals. But in addition to these 0-1-1 integrals, we found another interesting thing in an impact diamond. We found an integrals between diamond and graphite. Now I'm talking about crystallographic integrals, so not just a simple mixture of diamond and graphite. And we named it diaphyte because diaphyte was already used, this name has already occurred in the literature in 2009. Japanese scientists demonstrated that on the graphene layer, as a result of photoexcitation, these diaphyte layers form. We just extended this definition to three-dimensional materials, and we find out there are actually two diaphyte types, depending on the integrals between the graphene and diamond layers. And here in this slide I'm showing the first type, which is actually we are seeing the 1-1-1 diamond layers and graphene layers on the top of this diamond, on these diamond layers. And if you want, you could say that there are two diamond layers. There is the interface, that's the blue region, and there are three graphene layers. And if you want, we could, you can envisage lots of members of this diaphyte 1 family. However, the issue which I would like to point out, they are not ordered, so we didn't see like three diamond layers, three graphene layers in a repetitive order. So anyway, so this is the first type of diaphyte. However, we find out there is another integrals, which again occurs between diamond and graphite, which is called type 2 diaphyte. And now I would like you to point out on the slide on the top, that you would see that we are seeing diamond projected along the 0-1-1, and between these diamond domains, 0-1-1 diamond domains, there are graphene layers which are covalently bonded to this structure, and as a result of this strong covalent bonding, even the interlayer spacing changes. So in regular graphene, you may know that it's 0.33 nanometer. Here, due to this covalent bonding, the interlayer becomes 0.31 nanometer. And if you look at this structure in the perpendicular projection, you will see the graphene layer on the top, and you will see that they are bonded into the 1-1-3 planes of diamond. And here is on the left, on panel A, you will see the HRTM image that shows these type 2 diaphyte integrals. So they can be recognized as hexagonal rings. Now, there is an additional complexity to that. If you look at in nanodiamonds, we found these hexagonal rings, these type 2 diaphyte integrals. But graphene layers can be rotated on the top of each other, and they could form really interesting rotational symmetries. Here we are, if they are rotated on a twisted angle, they form this 12-fold rotational symmetry, which you will see on the right side of the image, which resemble the shape of a cacti. Anyway, so these are integral structure, the diaphyte structure. Now, even the different type 1 and type 2 diaphyte structure, they could intergrow with each other. So a type 1 diaphyte structure, we found that they extends, they continues into the orthogonal projection of type 2 diaphyte. Or we found even the type 1 diaphyte occurs on the top of type 2 diaphyte, which give rise to complexity and complex HRTM images. But when you consider these integrals, these different type 1 and type 2 different integrals, and add the stacking disordered diamond, then you will see images like what I'm showing here, which like almost doesn't show any periodicity. It's completely lost in the layer perpendicular to the third, perpendicular to the layers. So this is what I'm asking. So it's crystals is essentially sharp diffraction. Essentially, it's difficult to categorize them. So these images to me looks like when during crocheting, the knitting needle will slip the way in all directions. So anyway, these are examples from the Canyon Diablo diamond and shows evidence for the integrals of these stacking disordered diamond and diaphyte structures. Now, these diaphyte structures has very interesting properties, point of even mechanical and electronic properties. In particular, as you know, diamond is a very hard material, but not ductile. So it's not suitable for application which requires the diamond would be ductile, because according to calculation, ideal diamond could achieve even 45% longitudinal strain at a tensile stress of extremely high 200 GPa. However, in ideal diamonds, they break much before that. And in contrast, graphene can really reach 25% strain. So if we consider this diaphyte structure, which are contained within diamond, we could engineer this fracture-toughened diamond, and which behaves like a kind of ductile diamond. In fact, we gave the name that under tension, these diamonds behave like a mozzarella type deformation, and as a propagating crack, during extension, during breaking, the structure could absorb the energy of this propagating crack. And calculations demonstrated that as a result of extension-induced graphene formed when we apply extension. Another interesting thing is the electronic properties. As I mentioned, diamond is a wide bandgap insulator, whereas graphite is a conductor. So by building on purpose this diaphyte structure, we can tune the electronic properties of the material. We can prepare even nanoconducting materials. And from the geological point of view, it's also important because the recognition of this various type can aid toward understanding the pressure, temperature conditions during an asteroid impact. So I would like to summarize my talk that I think elemental carbon is really useful for studying. It forms a wide variety of forms and structures, and their study really brings us closer to understanding the formation conditions of meteorites, even interpreting astronomical signatures and discovering new materials for potential applications. And now I would like to acknowledge my co-authors who helped me in this work, and also the grants I received, and I also thank you for your kind attention.
Thank you. I think we have time for one couple of questions, if you, or comments. Please, Professor Bindi.
So, Peter, thank you very much. Very exciting. I have a question about Lonsleite, because I can see still a valid mineral species. So I read with attention your PNAS paper and then the Tomskins reply to your paper. So I would like to know if what is the status right now? Is going to be discredited or not?
Well, actually, you know, okay, so this is a different question. First of all, you know, as you know, there are only a few minerals which were named after women crystallographer. So this is a very difficult case. I think there are only 20 minerals. So we can't be so masculinist to discredit a feminist. So, I mean, the mineral, but being a mineral, we suppose a mineral consists of one type of structure. The problem is this is not one type of structure. It consists of this diaphyte structure and even this disordered material. So, as for sure, this is for sure for the type material, for what we find out. So even though this is not a mineral in the real sense, but as you know, in the Mineral Commission, they changed the rules based on that. Even so, the polytypes now they shouldn't have a new name. So there are many examples for that. It just comes out with zinc sulfide or whatever. So there are two names. So we are hesitant to describe as a mineral.
Okay, thank you very much.
Not a question is welcome, if any. Please.
So, thank you very much. It's the first time I heard this new term, diaphyte, so I never was aware about this. So do you think that it will be ever possible to replicate artificially this type of material?
Yeah, actually they occur, you can make them, but actually they exist in CVD diamonds. We found them in CVD diamonds, and it's, now the thing would be to make them on purpose. The problem is, as I should show you, so they are not ordered structures. There exist different the variations of graphene and diamond layers. It would be good to synthesize one type of structure, which is still not the case. Or maybe use, you know, another idea would be use lasers, you know, maybe to prepare CVD diamonds and treating with a special laser, practically preparing these diaphyte structures on purpose.
Yes, because I think that the most challenging task is the growth of bidimensional diamond-like layers.
Yes.
Okay, thank you.
I think we can close this session. Thank you again. And please come. I leave the word to the organizers. I must well organize.
Okay, so thank you very much. We are finished also this session. So I would like to say a few words. So thanking again all the speakers. So we have passed a lot of things, including discoveries, experimental techniques able to describe these kind of materials, also the mathematical applications, and so it was exciting. And so I think these kind of interdisciplinary meetings are wonderful in order to mix competence and try to explain brought back on the projects in different ways or with different ideas. At least this is what was my impression. I would like to say that in the next weeks I will contact all the speakers in order to ask your possible availability to write a paper if we were able to get the permissions from the Academy to have something like a volume dedicated to this workshop. It will be interesting because it was something like it would fix the memory of this meeting. I know that you are all very, very busy, so this is the reason because I will check your availability in the next weeks if you want to write something or not. Because if I get only the availability on a couple of you or something like this, it is actually not useful. So we are close to the lunch time, so it is time to finish this meeting. But I would like to ask if you have some comment or other questions, or you want to discuss something related to all the speakers present here today. This is the moment to do it. So if you have, yes, please, Arianna.
So some colleagues of mine were commenting that the word aperiodic is not a good word to describe something that it's actually periodic in more than than 3 dimensions. Any comments on this, or why? Because aperiodic can also be completely disordered, so it's really a broad term. Don't we have a better term for these wonderful crystals?
You mean for quasicrystals or in general?
Also the modulated crystals, so they are periodic in their mind. So it seems a bit a misnomer.
You mean it's restricted to a category of members, or because for aperiodic crystallography, I mean that I individuate modulating commensurate structures, composite modulated structures, quasicrystals, and you want to include something more there?
No, I'm just saying that the choice of the term seems to suggest that there is no periodicity.
I see.
But it depends on how you look at it, and actually we have more periodicity, if you want to say. But yeah, of course, this is a philosophical question.
Yes, you're right. Okay, so Lara?
I agree with Arianna, because how to call a glass material is an aperiodic material or not.
Okay, so, but in terms of diffraction pattern?
Okay, this is the point. So that's why I don't know if the correct term is aperiodic, because incommensurate crystals, quasicrystals show a clear diffraction pattern.
I think
this is the point.
I think, yeah.
The completely lack of periodicity means, in my point of view, okay, it means having an amorphous material.
I see.
Okay.
But you're right in a plane that I think that it could be an enlarged view, because recently a lot of people are describing new category of structures, including heterostructures or something like this, which are, it seems that they are in the middle between quasicrystals and amorphous crystals. So in other regions, intermediate there. So they should be included, absolutely, because they have a diffraction pattern. So I think that this is a discussion we should be brought into the International Union of Crystallography, sure. So other comments? Okay, so I thank you again for you to be here for these exciting discussions, and so I hope to see you in the next event soon. Thank you.